Hi, this is Isaac Schaefer, and this is my second video presentation for Math 431. Today we're going to work on problem 3 from lesson 7. We're asked to solve this initial boundary value problem with insulated boundaries. We're also asked to give an interpretation of the problem, find the steady state solution, and determine if it makes sense. So we'll start with an initial interpretation. Since the boundary conditions show us that the boundaries are insulated, that means that there's no flux of heat into or out of the system. And that actually ultimately means that there's no change in energy for any given time interval. And so we're going to basically have the energy in the system initially is going to equal the energy in the steady state. What this also means is that after we have this initial temperature, it's going to level out into some kind of constant function, where that is the temperature profile is simply just going to be some constant temperature throughout the interval between 0 and 1. So for step 1 of the solution, we're going to separate the variables. This is just like finding an arbitrary solution from lesson 5, and so we're going to skip that. For step 2, we're going to apply the boundary conditions to our arbitrary solution. So first note that the derivative, or I should say the slope of the temperature curve, which is u sub x, is equal to the negative lambda squared times a times lambda times the cosine of lambda x minus b times lambda times the sine of lambda x. When we plug this function into the boundary conditions, then what we find is that for x equals 0, a is equal to 0 or lambda is equal to 0. Now, the way to interpret this is that if lambda is equal to 0, then that means that our solution, on the left hand you might see, and you'll be able to see, I should say, is that means that the sine of 0 is equal to 0, which means that while we could choose anything for a, it doesn't really matter because the whole term here is going to be 0. And so we can discard the lambda equals 0 and just assume that a equals 0 for our solution. Now at x equals 1, the boundary condition yields that lambda is equal to n pi, where n is any integer. And this is pretty much just like what we would expect from previous lessons. And so the general solution to our problem is going to be the form of like this, is that it's going to be from n equals 0 to infinity of b sub n times the exponential of negative n pi squared times t times the cosine of n pi x. And notice that since we're using a cosine function instead of a sine function, we're going to start our index at n equals 0 because when n equals 0, the cosine of 0 is equal to 1. And so that term actually has information that we can make use of. Step 3, we're going to apply the initial condition. First, we're going to set x equal to our general solution when t equals 0. And then, as you may recall, we're going to then exploit the orthogonality of the cosine functions over the interval between 0 and 1. So for some non-negative integer m, we'll multiply both sides by the cosine of m pi x, and then we'll integrate both sides from 0 to 1 with respect to x. Now, we actually then have to consider two cases. In the first case, when m equals 0, then the cosine of 0 is equal to 1. And that means that our our equation simplifies to the integral from 0 to 1 of x dx, which is equal to the integral from 0 to 1 of b sub 0 times the cosine of 0, and then all these other terms from the series. And then we're, of course, integrating with respect to x. Now, on the left-hand side, that simplifies to 1/2. Now, on the right-hand side, there's a bit more work, but it's pretty easy to actually get through. So for the first term, we have b sub 0 times x, which simply just becomes b sub 0 once we actually evaluate the integral. Then the series itself is also being integrated from 0 to, or evaluated from 0 to 1. Now notice when we plug in that 0 that becomes sine of 0, and then when we plug in the 1, we get sine n pi. The thing is that both of these terms are actually equal to 0, and so that means that the entire series is 0, and thus we're left with just the b sub 0. And therefore, we can conclude that the first term in this series of b sub 0, or I should say the first coefficient of the series of b sub 0 is equal to 1/2. All right, step 3. Now we'll continue to apply the initial condition. So if m is greater than 0, then our equation on the right-hand side simplifies to 1/2 b sub m, which is actually pretty much how it's always worked in all the previous solutions. And so now what we're going to do is simply multiply both sides by 2 and then solve the left-hand side of the equation, which is 2 times the integral from 0 to 1 of x times cosine of m pi x dx, which is equal to this big ugly expression I'm not even going to try to explain. And then at intex simplifies to this expression. Now what we have is 2 divided by m pi squared times -1 raised to the mth power minus 1. And the way to think about this is that if m is odd, then that term, the -1 to the m, actually will become simply -1, which means that the coefficient is equal to -4 divided by m pi squared. Now, on the other hand, if m is even, then that means that this term becomes just +1, which means you have 1 minus 1, which evaluates to 0, and which means that the coefficient is 0. Okay, and so now we'll summarize what our solution is, which is that we have 1/2 plus the series from n equals 1 to infinity of that coefficient we just computed times the e to the -n pi squared times t times the cosine of m pi x. Now, step 5. Here we're going to look for the steady state solution. So if we take the limit as t goes to infinity of u, and we evaluate of u, then what we find is that most of these terms are actually just constants. So for instance, the 1/2 is a constant, so the limit of that remains is just 1/2. And then with the algebra of limits, we can actually then continuously move the limit operator into the series and eventually actually move it into the exponential function. And then, since this function is well known to us, is that the limit is actually equal to 0, that means that all the terms in this series is equal to 0, which means that the series evaluates to 0, and therefore the steady state solution must be 1/2 degrees Celsius. Which gives us this graph here, which is that eventually, as t goes to infinity, then the temperature profile will be a constant 1/2 degrees Celsius across the entire rod. All right. So here we have a graph. It goes pretty fast. So what's going on here is that we start with the initial condition, and then, as you'll see, that the temperature profile starts to average out and approach from both ends. It's from the left-hand side, it's actually gaining temperature, and while on the right-hand side, it seems to be losing temperature. And then as we see it starts to level out and get to that constant function of 1/2 degrees Celsius throughout the entire rod. All right, so that's it. Thanks for watching. Have a good day.